Today's lesson, we're going to talk about trigonometry identity. We went over this 4 identity before. So just remember by going over what types of identity that we did. Pythagorean identity is especially important. This is reciprocal identity and quotient identity. You should be memorized by now by using them so much since the beginning of the semester. We do have even and odd identities. And using this identity, we're trying to see if we can verify identity. What does that mean? It means that we wanted to show that one side of the equations really equals to the other side, right? It said it is, but we wanted to show how this side is equals to that. So like proving, right? In order to do that, we're going to go through these 4 steps. The first step is going to be trying to pick which side you're going to work on it. Usually the complicated side, you're going to start working on it because you have more to do with that longer or complicated side. Once you pick which side you're going to work on it, all the term you want it to change into sine and cosine. Once you change all the term into sine and cosine, you're going to apply basic algebraic technique like factoring, multiplying, combining the like term, or writing fractions with the common denominator when they're asking to do addition subtractions, right? And so on. And then you also wanted to do this step 4, which means trying to apply fundamental identity, trying to apply any of this identity to see if you can go from one point to the other point. When you are using identity, you could consider these 3 points. Expression is a product or quotient of factor. Consider reciprocal or quotient identities. Square terms are present. Look to see if the term can be grouped in one of the form of the Pythagorean identity, because Pythagorean identity is the one that have all this square, right? And if the expression is involving the negative, then consider using the even and odd function identity. Even and odd function identity. Okay, so let's start maybe the first problems following that steps. So example 1A, I will probably pick this side is because it's longer, right? Longer. So if I pick that side, oh, that's red. So if I pick this side, once I pick the side, remember I'm going to change it to sine and cosine trig functions. So secant is the same as 1 over cosine x times cotangent is going to be cosine x over sine x. 1 over tangent. Cotangent x is 1 over tangent, which is cosine x over sine x. And you don't have to write this, but this is equals to also 1 over sine x, right? So then you know this multiplication, you can get rid of the common factor, numerator versus denominator. So it gives you 1 over sine x, which is same thing as that, cosecant x. So that's how you can prove this side is equals to the other side. So if we're looking at the second one, you're going to pick the left side again because that's longer. Longer have something, longer one have something to work, more things to work on it, right? So the first one is sine x times tangent x. Sine is already sine. Tangent is equals to sine x over cosine x plus cosine x. And this is multiplications and additions. So you do multiplication before. When you multiply this two, because sine x is same as sine x over 1, so numerator multiplied by numerator, give you sine square x over cosine x. And don't forget you have plus cosine s before. And then what you wanted to do is you wanted to do these additions, right? These additions, in order to do the addition, you have to have same denominator. So this one, when you multiply by cosine x, you need to multiply this by cosine x, so this becomes square. And now you have same denominator. To add the numerator, you have sine square x plus cosine square x over cosine x. And this is your identity, right? That will be Pythagorean identity. Gives you equals to 1. So it's 1 over cosine x, which is same as secant x, right? So I can prove this side is equals to the other side. Let's try another one, C. Again, I'm going to pick the left side because it's just more to work on, longer. You have cosine x times cotangent. Cotangent is cosine x over sine x plus sine x. Again, you do the multiplications before additions. So that gives you cosine square x over sine x and plus sine x. That makes the same thing as the other problem where you need to have a same denominator. So you multiply numerator, denominator by sine x. Numerator become sine square. This, when you add it, because you have same denominator, you should be able to add it. It gives you 1, which is 1 over sine x. And this is equals to cosecant x. D, I will work on the left side and look like I have common factor x. This one I don't have to change to sine and cosine because it's already all cosine and cosine. I get 1 minus sine square x. Remember, whenever you see square, you're going to use the Pythagorean identity. And this is going to be same as cosine square x. And when you multiply this gives you cosine cube x. And that's what you have on the other side. Okay, so example 2, we're doing the same thing again, trying to prove the both side is equals to each other. So this is fractions. So I like to work with fractions first, then and especially when you have all sine and cosine there, right? This I can separate into 2. Why do I decide to separate into 2? Because the other side is 2 term. So this fraction I should be able to separate it into 2 fractions. And when we do that, this become 1 over cosine x. We know that's equals to secant x. And then you have sine x over cosine x, which is going to be tangent x. And that's the other side. And B, I will start working on the left side because I have two fractions. It means I'm going to trying to do combining because the other side having one term, probably that's what I would be able to make one term by adding those two fractions. In order to add the fractions, you have to have same denominator. So let's see, same denominator on this one is going to be 1 plus sine x times cosine x. So if this become least common denominator, this first fraction's numerator, you need to multiply by cosine x times cosine x. And this numerator, you need to multiply by 1 plus sine x also. This means you're going to get cosine square x plus, you need to do multiplications, right? Which you FOIL them, you get 1 plus 2 sine x plus sine square x all over same denominator. And what do you know about the numerator? What I recognize is having cosine square x plus sine square x. This is a Pythagorean identity, which is going to be equals to 1. So this 2, you can rewrite. This 2, you can cancel it and rewrite just plus 1. And you have plus 1 here before. So you can add that. And you get 2 plus 2 sine x remains on the numerator only. And the same denominator, you should be able to write it as cosine x times 1 plus sine x, which is the same as this, but looks cleaner, right? And then what else we need to do? I will factor the common factor 2 out. Then I get 1 plus sine x and with the common denominator. And part of the common denominator is also on the numerator, so you cancel out each other and you get 2 over cosine x, which is 2 times 1 over cosine x, and that gives you 2 times secant x, which is the other side of equations. And this proves that left side is equals to the right side. Since C is similar to B, I will skip that and do D, right? So if I work on this problem, starting with the left side, I have sine x over 1 plus cosine x. I mean, I cannot do anything, right? The left side is one term, right side is one term. What else can we do, right? What I will do in this problem, because I cannot do any additions, subtractions, multiplication, divisions, I'm going to start multiplying by conjugations of denominator. Again, reason I'm doing that is because it's already all sine and cosine, no factoring needed. I don't need to do any additions, subtractions, multiplication division of fractions. So, I wanted to see what I can get if I multiply by conjugations of denominator. So conjugations mean the same thing as denominator here. It's just instead of positive, it will be negative. That's the conjugations of denominator. And then I will get sine x times 1 minus cosine x. Denominator will be 1 times 1. You need to do foiling, right? So it will be 1 minus cosine square x. The middle term cancel out. And because you have cosine, 1 minus cosine square, 1 minus cosine square, that's the Pythagorean identity. So because the square, what I can do is change that into sine square x, right? Using the Pythagorean identity. This is equals to that. That means I create a factor, common factor here, and just cancel out. I had 2 sine x on denominator, so only one will cancel out. I will get 1 minus cosine x over sine x remains on denominator, which is going to be the other side of equations. So don't forget, if it's a fractions where you have nothing else to do because it's already or simplest form, and it's all sine and cosine, trying to multiply by conjugations of denominator and see if you get the other side. This E problem is the same thing, right? So now we're going to work on example 3. Example 3a, I will start working on the left side again. And I have the negative x. So I'm going to use even and odd functions, identity. And tangent x, I'm going to change that into sine x over cosine x. And sine is even functions, even trig functions, so it will be just, sine is odd, right? So that negative become this minus change, so it will be plus sine x over 1 plus cosine x. So again, if I show you how I change this to the additions, negative sine negative x is negative sine x, which makes this 2 negative positive, right? So that's how I got this. And then I need to do addition. It means I'm going to make the same denominator by multiplying numerator and denominator by cosine x. And when I add it, I get sine x plus sine x times cosine x all over cosine x over 1 plus cosine x. So this is complex fractions. And look like this. You have a common factor. You're going to factor sine x out. You get 1 plus cosine x over cosine x. If I wanted to pull this 1 plus cosine x, this complex fractions, second fraction denominator onto the side, it means you're dividing this by 1 plus cosine x, dividing by, right? And you know that divisions, you can change to multiplications. And flip the second fractions. This gives you same denominator. And numerator cancel out. Only sine x over cosine x remains. That gives you tangent x. So that's how I can prove this left side will be the same as this right side. Let's see if we can do problem B. It's similar problem, so if I start with the left side again, I have secant x minus cosecant x over. So what I can do is separating this into two fractions. Why? It looks like I have two terms on the other side, right? Then I get secant x over secant x times cosecant x. And then this is going to be minus because cosecant is negative functions. And then you get cosecant x over secant x cosecant x. When you get rid of common terms, you only get 1 over cosecant x minus 1 over secant x remains, which is same as sine x minus cosine x. This time I didn't change to sine and cosine because if I change to sine and cosine, I will have complex fraction. I will have fraction over fraction, everywhere fractions. But at the end, I will end up canceling out those values. So I keep it as it is to make it not complex fraction in the fractions. If we're looking at problem C, I can start with the left side again. So if I start with left side, same denominator is what I need to start it because I need to do additions. So if I make same denominator, least common denominator will be 1 plus cosine x times 1 minus cosine x. It means the first fraction I need to multiply by 1 minus cosine x. And the second fraction numerator I need to multiply by 1 plus cosine x. And when you simplify that, you get these two cancel because 1 with the negative, 1 with the positive. 1 plus 1 is 2. And when you multiply this FOIL, I get 1 minus cosine square x. And this is equals to this square is Pythagorean identity. So when you convert that, you get 2 over sine square x. And I don't know what else I can do to this to make that, right? So then what I can do is, instead of guessing what I need to do, let's see what I can do on this side, right? That side is also kind long, I can work on that side and see what I can get. So I will factor 2. Then I get 1 plus cotangent square x. And we wanted to make it sine and cosine. So it will be cosine square x over sine square x. And you need to do additions. So this 1 will become sine square x over sine square x, right? So then you can add it because you have same denominator. It means your numerator will be sine square x plus cosine square x over sine square x. This numerator right here is Pythagorean identity, which means this numerator is equals to 1 over sine square x. When you multiply this is what you get, right? So in other words, you could go this directions and get here, backward, right? So this is how you can prove the left side is equals to right side. And sometimes you need to work both sides to get in the middle. Problem D is similar problem as C. So I will skip that. And if you wanted to see the work, make sure to check my class notes.